last sessions for today, and the first talk is of Vassili Kolokoltsov. It is very pleasant for me to introduce Vassili Kolokoltsov. The talk is, can you show us?
Yes, I think I can. I think I can.
А вот тут надо нажать дополнительно, и там будут показать экран и так далее. Вот тут есть среди четырех, вот тут дополнительно. Угу.
О, видите, да?
Да, видим. What is the title, this one?
Ну, это вот title and abstract. So
okay.
everything is in, yeah? Yeah, I can start, yeah? You see me, yeah?
Sorry?
You see everything, so I can start, yes?
Yes, we can see what is...
Okay, fine. So unfortunately, I did not manage to prepare specific slides for the talk, so I will just use two of my papers and explain using them. But you do not have to follow the text which is written, because I will mostly talk and just want to show you the equations. And all the words, I mean, will be set separately. So this is the title, Dynamic Law of Large Numbers for Quantum Stochastic Filtering and Related New Nonlinear Stochastic Schrodinger Equation. So some general words, first of all, because there are several kind of links here and several developments. I just want to say, to explain one bit of it. So there is a very popular activity in quantum physics in generally is to see what happens when there are many particles identical when they interact. What happens when the number of particles tends to infinity. This is some kind of quantum analog of the law of large numbers. And this activity was started by Schrodinger himself, and he understood that in the limit, if we have large system of interacting particle, which is pairwise interaction, then in the limit of the number of particles to infinity, this system decouples, and each particle follow its own individual Schrodinger equation, which is, however, non-linear. So there is non-linear Schrodinger equation appear. And there first, also this equation has different names, so it's sometimes called Pitaevsky equation, sometimes Hartree-Fock equations. There are various versions of the same, but they all are of the same kind. There are, first, of course, they were developed by physicists and somehow very vague, I mean, not a rigorous, but there is a rigorous version, in particular by Pitaevsky. And first, I suppose, first rigorous derivation somewhere in 80s, so about 40 years ago, first rigorous derivation of this equation is really as a limit with everything proved. And recently, actually, in our century, there just 10, 15 years ago, actually, there was a big flux of papers with rigorous derivation under various more realistic conditions. So the first proofs were effectively when potential is bounded. Now, for now, it's developed for very general cases, really potential, which covered Coulomb interaction and so on. So this is one direction, nonlinear Schrodinger equation. Another direction is stochastic Schrodinger equation and stochastic nonlinear equation. And I will also show some mostly used equations which appear in the theory. So now my path and my point will be some new kind of nonlinear stochastic Schrodinger equation. So I'm going to derive new equation, which is nonlinear stochastic, but it's different from those nonlinear stochastic equations which were considered so far. And I will explain why. So the path to this derivation goes through the theory of quantum stochastic filtering. So some words about it. quantum stochastic filtering was developed again about 40 years ago. There are many people who took part in this, and this was done in the community of open quantum system and mathematically speaking quantum probability. But the main derivation, nevertheless, was given by Belavkin, and therefore this equation is usually called Belavkin equation or Belavkin filtering equation. I'll show it in some of this form. So it describes you the following thing. Assume, so usual Schrodinger equation is about closed quantum system. Yeah, so it develops somehow, yeah, and we are not doing anything. We are not doing anything. It develops on its own. And everybody knows that in quantum physics, if you try to measure something, if you make some observations, then you destroy the dynamics. Yeah, so you cannot just look at what's going on there. It's this famous paradoxes of Schrodinger cats and so on. So nevertheless, there is a theory which allows you showing some tracks. For example, if you see a particle in clouds, Wilson camera of clouds, some other tracks, so you can reconstruct the dynamics of the particle, and this reconstruction is precisely given by this quantum filtering equation, Belavkin equation, which was developed, Belavkin and proved somehow mathematically, and it was also suggested parallel by some physicists who somehow just guessed this equation from certain various physical principles. So this equation, for me, the reason for developing this theory. So what I'm going to look now is to consider the system of many particles, so law of large number, which interact pairwise, and they are also observed continuously. Yeah? So they satisfy this quantum stochastic filtering equation and see what we get in the limit. And in the limit, we get this new kind of nonlinear stochastic Schrodinger equation. For me, the reason to start developing this theory was actually also another recent story is the story of mean field games. So this is the most popular branch of game theory now, developed about 15 years ago, it appears. And I wanted to understand what should be quantum mean field games. And this was actually this limit was the main step into the direction of this quantum mean field games. I will not be able to talk about them, but I will use this my paper in analysis of probability devoted to this quantum mean field games, and I will use it. So this is a paper which was published last year in the Annals of Applied Probability, and I will use this paper to explaining the idea, how one derive this nonlinear Schrodinger equation, and maybe a couple of other papers, depending on how much time I will have. So if you have, by the way, any questions, then please do interrupt me. I'm really always welcome the interruptions, the discussion. I like questions so that everything will be clear. Okay, so what I'm going to say, first of all, I just want to briefly introduce you to this quantum stochastic filtering. And therefore, I'm showing you this equation. So this is equation. This will be my starting point, this equation. And let me try to get my pointer. I'd like to get a pointer. Pointer. Yeah, so look at this guy. So this is the main equation of quantum stochastic filtering. This is somehow Belavkin equation in one of its many actually versions and many forms. So for those who see this for the first time, I just want to give some explanation. So if there would be no this right thing, only this. Yeah, so this is kind of standard Schrodinger equation, just self-adjoint operator multiplied by I. Now we want coupling with the observed trajectory. Observed trajectory is some kind of diffusion. So this is kind of Brownian motion. How can we make coupling? Well, just some operators. So this is coupling operators. So we add this stochastic part to the equation. And now where this thing comes from? Now, yeah, and that's how this equation actually was guessed by physicists, I suppose. They say, well, this is usual Schrodinger. Now we add this noise based on the observation. Yeah, so this YT is called the output observed process, diffusion, Brownian motion, if you like. But what do we want from this equation? So from physical, several physical considerations, we want to have an equation actually which preserves the norm of the solution. But it turns out that in this stochastic version, this is really impossible. But what is possible is to make the preservation in the average. So we want here some correcting terms such that the square norm is preserved in the expectation. So in other words, the norm squared is a martingale. So now if you play with eta formula, then you can find out that it should be like that. So what is what here? H is self-adjoint operator, arbitrary. L is an arbitrary operator, self-adjoint or not. And L star, of course, is the adjoint operator. So we observing this YT. This is what we observe. And this is Brownian motion. And based on this observed YT, we can reconstruct this chi solution. Yeah? So this is Schrodinger equation describing the particle under continuous observation. Now, it was out the theory of quantum filtering that rather than this YT, more natural is the process dBT, which is linked by this nonlinear, yeah, because this is the average of the operator L plus L star. This is the definition, usual definition of the average. So it nonlinearly depends on chi. So this dBT, and it's called innovation process from the physical point of view, it is more natural. Sorry. From the physical point of view, it's more natural. Sorry, I have to answer. Да, здравствуйте. Ну, он мне этого пока не говорил, но, в принципе, сказал, что запишет, да. Хорошо. Угу. Ну, это, конечно, поздновато. А чего пораньше нет? Ну, хорошо, ну, что есть, то есть. Сейчас я, секундочку, я буду. Да. Хорошо, да, пожалуйста, позвоните, знаете, я должен сейчас прекратить. Я не могу разговаривать сейчас. Пожалуйста, тогда вот на день вы накануне позвоните, тогда все расскажете мне, да, но мы договариваемся. 7 на 6 часов вечера, да? Все, спасибо. I'm very sorry that I have to interrupt because this is because from a doctor. It's an appointment. Okay, so now where I stopped, this is the version of this thing, yeah, when we have several observations. Yeah, so this is just sum of the thing, and here will be the sum of the thing, all is the same. And therefore, this is a multidimensional Brownian motion and another multidimensional Brownian motion, which is called innovation process. So one can write equation in terms of this dy, in terms of this dB, and there are various versions of the equation which you can get here. Now the next important thing. We know that in quantum, sorry, I'm closing the door. In quantum theory, one can describe the quantum states in two ways. There are more used one, which usually learn in schools. One describes the state of a quantum system by a unit vector in a Hilbert space. These are so-called pure states, but there are also mixed states, and these mixed states are given by the matrices, positive matrices of trace one. So we can also think about evolution of quantum system on the level of vectors in the Hilbert space or on the level of matrices in the Hilbert space. So this is the corresponding version of this quantum filtering equation on the level of density matrices. And I remind you that if you have a vector, and to each vector chi, if you take chi tensor chi bar, and this will be precisely the matrix, density matrix, which corresponds to this vector. But this is decomposable matrix, which decomposes into the product, but not all matrices necessarily decompose to the product. Yeah, so another version, therefore, of this Belovkin equation is in terms of matrices. Now, there already here, you may note possibly the difficulty which arises here. And this, I can stress that, in fact, my talk suggests several open problems. I'm not sure actually what is the progress so far about anything serious about this equation in general. So the point, maybe there is something, but possibly just recently. Yeah, because if you consider equation in the Hilbert space, then it's fine. We have the whole theory, Ito isometry, everything works fine in the Hilbert space. But if you try to build the theory of stochastic equation in the Banach space, then, you know, if you start, you quickly realize there is nothing is very easy there. And in fact, there are lots of very big and very technical papers about the stochastic equation in Banach spaces. And they're usually done for certain, so to say, good Banach spaces, which have different versions, these good Banach spaces. Something like reflexive is actually good, for which the natural theory develops. But this is not in any way good space. Yeah, this is a space of trace class matrices. Yeah, so this is some kind of quantum analog of the space of measures. Yeah, they're not reflexive. So this is a bad space. So if we talk about finite dimensional story and finite dimensional quantum mechanics, then there, of course, no question with this equation. But if we are talking about infinite dimensional, then already sort of well-posedness for this equation is not very obvious. Now, important thing, if you take expectation of this thing, yeah, then you obtain very well-studied equation, and this is also very famous equation in the theory of open system. This is so-called Lindblad equation, and it also has different names. This is, in fact, the general form. Now, since we're now in this semi-group conference, therefore, I'm stressing this, yeah, that this is a general form of equation which generates the so-called totally positive semigroup in quantum mechanics. Yeah, so this is this famous Lindblad term. Yeah, so this is the usual kind of Schrodinger equation, and this is addition arising from the interaction of a quantum system with some open environment, and it depends again on this coupling operator L. This is also one of the ways to guess the stochastic equation. We have just to guess an appropriate correction term here, such that it can be put back on the on the level of the vectors. So that was just the general, more or less, words about quantum filtering. And I'm showing just one way of writing this equation. There are several other ways which I'm not touching. Now, so as I say, this is somehow first starting point for my research. And the second point, I'm talking about nonlinear stochastic Schrodinger equations. So these are the kind of equations which are actively studied in the literature. So this is again usual Schrodinger path. Now we have some nonlinearity with term dt, some nonlinearity with term dw. So this f and g, some nonlinear functions of vectors. And so most of the equation, I actually do not know any other equations of other forms than this. So there's quite a lot of activity. Röckner and many people around him studied equation of this kind. Now the stochastic nonlinear equation, which I'm going to derive and to present, is of different kind. So nothing from the theory developed to this, what is called stochastic Schrodinger equation nonlinear, will not be working for my case. So now we move, as I say, to the interacting particle system. I remind you, I told you at the beginning, if we consider many identical particles, quantum, which interact via pairwise interaction, then in the limit, this theory, this system decomposes into the individual equations. So what do we mean by interacting individual particles? We mean the following. Usually, they are given by the Hamiltonian, by the operator, Hn, of the following kind. These are sum of individual operators, identical. So we have some operator H, and the index J here means that this H acts on the J's coordinate. And then we have functions depending on pairs. So this is multiplication operator on function depending on the pair. This is a standard Hamiltonian of pairwise interacting quantum system. Okay, so now we can write the corresponding filtering equation to this system. So now this is our Hamiltonian, and I've just written the equation which was written in general way, this general quantum filtering equation. If you observe each particle by the same operator Lj, and this kind of text of each particle there can be considered as independent Brownian motions. So now my question, and this is what I'm going to present you today. So what happens with this thing when n tends to infinity? So I'm posing the same question as for the case without stochastic. So the standard theory would be without this thing. What happens? So what happens actually will be a new kind of equation. Now this equation is written for vectors, and I can also write it in terms of density matrices. And you may tell me, well, actually, why bother ourselves about these matrices if with vectors everything is much simpler? Well, simple in which sense? That there's no problem here with well-posedness. And for equations on the level of matrices, already well-posedness is not so obvious. So the question, the point is that actually all the proofs of the convergence, they can be naturally performed on the level of density matrices. And the proof of well-posedness, they are better done on the level of vectors. Therefore, I really need this version for matrices, because without it, I just cannot give the proof of any convergence. So this is this equation on the level of matrices. So in other way, how we can derive it? If psi satisfies this equation, if we just take the tensor product, psi by psi bar, then we'll see that this guy will satisfy this equation. Yeah, and again, if there will be no this stochastic term, this will be the Lindblad semigroup generator generating a semigroup of totally positive transformation of interactive particle system. So here, actually, we talk about Hilbert space H, which is L2 on some X, and X can be RD, or it can be some finite set. Yeah? These are things which are of interest. Now, I'd like to remind you how the people are getting this nonlinear equation classically, as was done by Fogg, Hartree, Pitaevsky, and many others. Yeah? So how we get nonlinear equation without this additional thing? So assuming L0. Now what we're saying, we assume that the solution can be written approximately as a product of individual functions. And this is in fact the main somehow heuristic part in this kind of character. Assume that it can be written as a product. That's what one actually has to prove rigorously mathematically, and this is difficult. Now, each J's particle will be influenced by the average interaction potential produced by all other particles. But distribution of the position of the M particle is the density. This is a famous Born rule for which he got his Nobel Prize. Therefore, that's what we get. That will be the potential acting on particle J. Yeah? It will be integral sum over all particles and integral over all the densities. And then, since they are all identical, and we'll get this thing. Therefore, this will be effective potential. And that's the equation which we get. And this is this nonlinear Schrodinger or Hartree-Fock and so on. Yeah. So this V psi t squared is just V applied to psi squared. And you see here this nonlinearity arises. Now, if we have this, so there is particularly useful case when V depends only on the distance, and therefore here then you get the convolution V with this psi square, and in this form usually this equation appears. Now, what happens in our case, which I'm going to discuss with you? Here we cannot say that all functions, all solutions will be identical. They cannot be identical, because the noises are independent. But what we can expect is that this psi j, they are identically distributed. And therefore, according to the strong law of large numbers, we may conclude that there exists this average limit of this density, which is the expectation, and which will be the same for all, somehow for the limiting situation. And therefore, we can now conjecture the limiting equation which will appear. So this is the main guide which I'd like to show you today. And I will formulate the rigorous theorem about it. So, but that's what we are expecting here. That in the limit, when the number of particles tend to infinity, the system decomposes. So the wave functions of n particles is represented approximately as the product of individual, and each one is developing according to this equation. So you see specific case which is not appeared in the standard study of nonlinear Schrodinger equation. Well, this is standard, this is just linear coupling with the noise. Here we have nonlinearity, fine, it's also appear in standard thing, but here we have new thing. This linearity depends on the expectation of the solution. So here we have something which can be familiar to people working with Markine-Vlasov equation. So this In McKean-Vlasov equation, we have nonlinear equation measures, yeah, depending on the expectation of some function with respect to this measure. Here is not exactly the same because this is not measure, this is amplitude, yeah, and this is measure. So here two things are different, amplitude and the measure. But if we turn to the matrices, that's why the matrices are in fact more natural, then the correspondence with McKean-Vlasov becomes much more apparent. Now, if I rewrite this for the matrices, then matrices, and this is the expectation with respect to these matrices. Yeah? So now if we consider matrices as analogs of measures, and this is how matrices in fact considered in quantum probability, analog of measures is trace class operators in quantum physics. Here we have exactly the same thing as for nonlinear McKean-Vlasov system. Yeah? So we have matrices instead of measures, and there are expectations with respect to these matrices. So you see, we have here, one can look at this as infinite dimensional, complex valued McKean-Vlasov equation on very special Banach space, actually on the Banach space of trace class operator. Well, so I'm going to formulate you soon the main result. So the main result will be anyway that our under certain assumptions, yeah, the solutions as n tend to infinity will be approximately given by the product of this gamma. So this is kind of main result told in general words. Yeah. So there are some additional complications. For example, for the control theory, it's also important to have this H and V, possibly depending on some control, or L. Yeah? So this is additional extension, which is really of importance. Yeah? But this again can be included. Yeah. So here I'm stressing this thing. Yeah, in this paper I considered simplified versions, but this only in this paper. Yeah, I have also. So this condition is just simplifying, but it's not necessary, and I can prove everything without the simplifying assumption. Therefore, I'm not stressing it here. It's just in this paper. Now another I will tell now about some extension modification. You see, I have considered the pairwise interaction by operator, which is multiplication by function depending on two variables. This is natural for continuous quantum mechanics, but for finite dimensional quantum mechanics, much more natural are operators of this kind, yeah, given by these matrices, depending on two parameters. Yeah, actually, these are the operator from function of two variables to function of two variables. So in order to get here, reduce it to the previous case, it should be diagonal, x prime and y prime. So if this thing is diagonal, then we reduce everything to the previous case. Anyway, so just in this case, we have slight modification. So the interaction becomes like that. So these are this A, I, J. So these are operators A applied to variables I and J. So they are more general than multiplication by V. They are integral operators. But everything else works fine. And in fact, it turns out that in this formulation, the results and proofs are a bit simpler than for the multiplication case. No, anyway, this is in the formulation. This will be the equation for the wave functions with this nonlinearity. You see, nonlinearity now appears in this way. So it is nonlinearity at least depend linearly on this thing. So it's a bit just simple. But this nonlinearity is again of the same kind. So this is expectation with these matrices. Well, so this is a corresponding Lindblad equation. nonlinear Lindblad equation arising as a limit. I don't know whether anyone derived it before, but this is just if we forget about all the stochastics here, then we'll get the same story for just for the deterministic equation. And there will be again this nonlinear kind of Lindblad equation. So this extends to many calculations. Now, a couple of words about the approach. So there are many now ways of rigorously proving this nonlinear stochastic, nonlinear Schrodinger limit. And really in 2010, 2015, this is just a big chunk of new results, so very strongly developed this theory in the last 50 years. So I am using one of these approaches, which I'm taking from the paper of Pickle. So his approach to proving this limit is based on considering the following numbers. You see, we want this. So this gamma is our solution. We actually want this gamma to be the product of this psi in the limit. So if gamma is the product, then this thing is 1, and this 1 minus 1. So if gamma is product, so that's what we want to have, yeah? Then this E, K, and T should be 0. And so the way to estimate the deviation of our solution from the product, we can just look at this number. So this is Pickle's approach. It's again appeared about 10 years ago, so it's again quite a recent story. But precisely this approach is very useful for this for the stochastic version I'm using. Now we cannot use, by the way, just as a comment, this gamma NT1K, this is so-called partial trace. What is partial trace? If we have a kernel operator with some kernel, depending on n variables, and if we take partial trace, we just take integral over all variables not equal to this, not belonging to this I, and therefore this reduces the kernel on n particle states to the kernel on k particle states. Yeah? Partial trace is a very important notion in quantum physics, and this is kind of way of looking k particle out of 10. And if we take trace on one particle, then this will be just looking at the individual behavior. Well, so this is the inequality proved by Pickle, that the case deviation for k particle is bounded by the deviation for one particle. Therefore, the whole proof you need is just one particle deviation. What I want to draw your attention to is that in our stochastic case, these actually things, they are not defined as they are, because now these deviations, they are individual. They depend not only on the number of particles, but on the individual particle, because all these guys are different. So from the first sight, you know, everything is falling apart. Yeah? But what we can observe is that if we take expectation, and by IID property, expectation will not depend on it. And that's actually what we're, so this is stochastic version of this I, but we want the expectation. And the expectation will not depend on individual particles, will not depend on I, only the size of I. And this actually is the things which we are going to estimate. So the technique of proving everything, in my approach, which goes back to the stick Pickle, is to show that these guys are small. And as they t times to infinity. And we also can see that if we know that they goes to 0, then this is also inequality due to Pickle, which tells you that actually trace of gamma minus gamma decomposable, our solution, is actually small. If this is small, then this is small, and there we have that this converge to this in trace norm. That's what we want. Okay, so that is therefore the theory. consider the main result of my talk. We have this operator HL bounded. Well, actually, boundedness is not important. They can be unbounded. We have V, which is bounded. Or there are two versions. One is a multiplication by V, or we have this symmetric self-adjoint integral operator with Hilbert-Schmidt kernel. So there is two versions. This is bound. So either this operator of pairwise interaction or this operator of pairwise interaction. So this is not important. I mean, just in this paper like that, but this is not really the case. But we have the estimates. You see, explicit estimates for this alpha n t, which measures the deviation in the trace norm of the solution of many particle system, to the solution of the product of individual solutions. And this is the bound, and you see this square root of n, 1 over n. And you see that in the case of this operator A, everything is much more simple. Here, in case of V, there appears this unpleasant integral, and I actually never thought it out. I mean, there should be some condition here which will ensure that this guy is bounded. I didn't really completed this properly. So here it's somehow assuming that this is bounded, then we have the estimate. But in case of the integral operator, everything is much simpler. Okay, so comments here. Again, apart from this, another interesting thing is that I assume that V here is bounded. Now, in the deterministic case, now V are much more general. They are allowed to be L2. So what can be here said for V which are unbounded? This is open question, which I consider as very interesting one. Now, another extension which I have done is the consideration H plus some control Hamiltonian. What can we say then? And then, well, this is now the version of the equation with control Hamiltonian. And we now allow this control to depend on the corresponding partial trace. So J's particle chooses the control based on its own trace, which is, of course, very natural. And here we have generalized equation. Now, the new point is the dependence on this control thing. But everything again goes fine, but we have to assume, which can be expected. Yeah, of course, we have to assume that the control is chosen as Lipschitz function of gamma. And it is, of course, very natural. If we have coefficients which are not Lipschitz, then difficult to expect anything. But this actually is very unpleasant for the application to the mean field games. But then we really have to reduce all our possible control to this additional restriction. Otherwise, nothing is working. Okay, so I have left, I suppose, six minutes. I'm not going to application to mean field games. This is another story. There is a very so as I say again, open question concerning the well-posedness of equation in this Banach space, and everything can be done properly for finite dimensional cases. And at the end of this paper, I actually show that everything works for finite dimensional system, which are very natural for quantum control and quantum games. In the last 5 minutes, which I would better say, I want to say about another type of filtering and another type of observation. Again, this Belavkin quantum filtering theory, it turns out that there are two kinds of continuous observation. One is when we really look at the trajectory. So this is diffusive or homodyne. It's called diffusive or homodyne. continuous observation. And there is another type of observation which is discrete. We actually assume that the particle, when it's moving somewhere, emits kind of photons, or particles, and we just register the number of particles which arrives at certain screen. And to this observation, there correspond an equation, also quantum filtering equation. Quantum filtering equation of different kind. So you see these terms are more or less the same, but here we obtain the jump type noise. And this noise is not very standard because this NJ, these are Poisson processes with intensities depending on solution. Intensity is trace. So this is a bit non-standard for the jump type process, but it can be actually easily reformulated in a more standard way, considering space-time here, white noise. So the point is that for this story, also the whole theory of quantum law of large numbers and quantum control and quantum multiple games can also be developed. So these are the equations. One usually writes the equation in terms of the compensated jump time process, martingale. We have this equation filtering, and in the limit, just attempt to show you that's the limit. So this is n particle equation, and I want to show you the limit. There is example finite dimensional, but I will skip it for no time, where everything can be calculated. So this is, I want to show you now this equation in the jump type case. So this is the interaction, and the same as it was before. And this is the version with the density matrix. And now there will be the limit. If we go to the limit, that's what we get. And so this is a nonlinear Schrodinger equation, stochastic quantum filtering. In the case of control Hamiltonian and control L, after it is in the limit of n to. And we also have the version for the density matrix. So as you can expect, instead of Brownian motion, you have here again this nonlinear jumps. Okay, so that's actually what I planned today, and just finishing usually just in time, I suppose, just 2 minutes earlier. So thank you for your attention. That's all I wanted to tell you today.
Thank you for your global report. Any questions and remarks?
Well, yes, I have a small question.
Please.
Yes, so in the abstract, there was mentioned something about fractional equations, a paper in fractional calculus and applied analysis. So what is the relation to fractional story?
Oh, there is another way to extend the quantum filtering. One can make, it's another equation which I've derived, some kind of fractional quantum filtering. And this is in another paper of mine, fractional version of quantum stochastic filtering. It's not about interacting particle, it's just about observation. So in fact, they are not in any way less legitimate than non-fractional one. In fact, you can derive this quantum filtering equation, as Belavkin derived it initially, it derived it using quantum stochastic calculus. So it's insightful way, but very complicated. And later on, there were suggested other ways of deriving quantum filtering equation just by the limit from the successive observation. Yeah. So, and for successive observation, you have this von Neumann postulate for observation. So you make observation, then dynamics, observation, dynamics, and the time between observations tends to 0. Yeah? So if you do it in somehow naive way, then you don't get anything reasonable. This is famous quantum Zeno paradox. But if you make some particular scaling of the dynamics between the observations, then you obtain this quantum filtering equation. But here you, of course, assume, as usual in all this Markov limit, yeah, that the time between this observation is exponential random variable. Now, if you consider this as not exponential, as people like in time random walk, and the time with memory, then what you get fractional analog of quantum filtering equation. So this is another, I think, very interesting direction in the sense that there is now classical fractional filtering, and I can show you the quantum filtering fractional control.
Okay, thank you.
And there should be a version of this thing for interacting particle system as well.
More questions, please. If not, I have questions about physics and mathematics in your talk, in your results. For example, if you consider equations in Banach space, is it has physical sense?
Well, of course, all equations are written on matrices. Matrices with a unit trace, they are basic objects in quantum physics. These are mixed states of quantum system. Therefore, Schrodinger equation can be lifted to this mixed state, and it is also used in physics. So yes, of course. In fact, these mixed states, they are more natural than the unit vectors. So it does make sense, but it is unclear mathematically. So I suppose so far there is no proper theory for these equations. And this is something I'm actually quite interested in. I had some project with some person, but we did not yet completed anything reasonable in this direction. But it's something which I am really interested to discuss. Yeah, equation in Banach spaces, and this particular Banach spaces, trace class matrices or measures, which are bad Banach spaces from the point of view of Ito, stochastic calculus.
And the same questions about, you mentioned our perturbations, not only Gaussian, not only Brownian motion, to my mind. What about different one?
No,
Poisson, to my mind, you mentioned.
Yes, there are Poisson and Brownian and diffusive, and there is nothing intermediate. This is very strange because for probabilist, of course, yeah, between Poisson and diffusion, there are the Slave processes, and they do not appear by some strange, I don't know why actually, yeah. But if you try to consider these limits, as I say, you make the time between observation tends to 0 and make some scaling in order to get reasonable result. So it turns out that you always get one of two versions. Depending on your scaling, you get either diffusive limit or the Poisson time limit, and nothing in between. I actually cannot properly explain that. For me, it's a bit also some kind of a puzzle. Why we do not get anything in the middle? But possibly it's precisely because of the physics that we either observe a track, which is kind of diffusion, or we observe, or we count the number of photons, and nothing and nothing kind of Levy can be observed. Yeah. Maybe. You can have mixed observations in the sense you can observe different channel. In one channel you can observe track, in another channel you can observe jump types, but nothing in between.
Mhm. Yes, thank you. More questions and remarks, please.
But probably this levies can be considered as a composition of different Poisson and diffusion. This is exactly like a superposition of Poisson. You get
Well, but then you
stable.
get some limit, yeah.
Yes.
Superposition, and you have to go to some limit. And what is the physical sense of this?
No idea.
It's unclear, yeah, because from this content of the problem, yeah, you get either this or that, yeah. Of course, you can write equation, but just generalize, yeah.
Probably
But,
if the amount of channels which you use for observations can also grow infinitely.
Yes, and these versions I consider, yeah, because we have number of particles to infinity. Each particle has its own channel, so here we have it, yeah. But to get it in such a way that you get this Levy thing, yeah, unclear.
Okay.
There. Any questions? When we have